Hello everyone, welcome back to lecture. We're going to cover 11.3 today, and it's basically, we're going to take what we learned last time from 11.1, 11.2, correlation. We went from correlation to the regression line, the slope, the intercept, and now we're just going to kind of focus on the slope and see if we can develop a confidence interval and then make a hypothesis that the slope is not zero, basically that we have a relationship between them, and we'll talk about it as we go along. So I'm going to get rid of me and let's get started. So inference on the slope of the regression line. So here's the assumptions of the linear model. So let's kind of get into this. The following table presents the number of calories and grams of fat per 100 grams of product for a sample of 18 candy bars. Basically, we have different candy bars here. Here's our product, and we've entered the number of grams of fat per 100 grams of product. And then here's the calories, the corresponding calories. Okay. So we basically can build a least squares regression line using technology, linear regression, the TI-36, we're able to do that. Remember, this kind of shows up in a couple of different ways. We could say AX plus B or A plus BX, but this tells us which one this is. There's the A. The A is the y-intercept, that's the standalone part. And here's our slope, the B is the 5.63. Our R value 0.964, and there's our R squared. That gives us an idea of the fit. The R value is the correlation. So when the points on a scatter plot are a random sample from a population, we can imagine plotting every point in the population on the scatter plot. Then as certain assumptions are met, we say that the population follows a linear model. Okay. So here we were talking about population. We've been talking about sampling up to then. So let's bring those two together. So here's a little b0 and the slope little b1 of the least squared regression lines are then estimates of a population. Here is for the population. Remember, our Greek symbols are always kind of indicative of population values. Here's a beta 0. So beta 0 goes along with our sample intercept B0. And our population slope beta 1 goes along with our sample slope B1. Okay. So in general, we don't have all the population values. If we did, we would go do the linear model with that, and that would be that. So we cannot determine the exact values of beta 0 and beta 1 because we cannot observe the entire population. However, we can use the sample points to construct confidence intervals and test hypotheses about beta 0 and beta 1. Here we're just going to focus on beta 1, the slope. Okay. So for our beta, we can make statements about beta 1 and then test it using hypothesis testing. And then we can also use our sample values to construct confidence intervals for the population parameter beta 1, the slope of if we had all of the population value. Okay. So here's the assumptions for a linear model. The mean of the value, so basically we're going to go down here. Let me kind of show you what these things are. I'm going to have our data, and then we're going to put a linear regression line. There's our linear regression line. If we cut these things up into little x value strips between here and here, here's the mean value of the y's within here. Okay. So the mean of the y values within a strip, as x varies, the values, the mean of y given some x follow a straight line, beta 0 plus beta 1x. The amount of vertical spread is approximately the same in each strip, except perhaps near the ends. Okay, so here's the spread between each one of these, and we've got some average value in there. Okay, the y values within a strip are approximately normally distributed. So this assumption is not necessary if the sample size is large. So it doesn't have to be approximately normally distributed. So here's our linear model equation. If we maintain all of those assumptions, we have a y is equal to beta 0. Now we're switching here. Usually we had been doing y hat is equal to a b0 plus b1x. And now we're saying that the population values are related to by x by beta 0 and beta 1. And within each little value here, there's some error. Okay, just basically some noise or something that has been introduced by measurement or whatever, but there's some random error. Okay, beta 0, that's the population y-intercept. Beta 1 is the slope of the line for the population regression. Okay, so the y-intercept b0 and the slope b1 of the least squares line are estimates of beta 0 and beta 1. Here is from the sample, and then these are basically our estimates of beta 0 and beta 1. So this sounds like if we have a point estimate of b1, we can use that to build a confidence interval for beta 1 and hence for b0. We're just going to focus on our b1. So how can we check assumptions to see if everything kind of holds to do what we're doing for a regression? So in practice, we do not see the entire population, so we must use the sample to check that the assumptions are satisfied. This is done with a residual plot. So here's the residual plot. This is what this is going to look like. I'm going to go, I've got a point xy, so this is the point from the sample. And the least squares regression line y hat is b0 plus b1x. So basically, I'm going to look at all these points that I know, and I'm going to look at the error, the residual. The difference between the actual and the predicted is the residual. Okay? So if y hat is equal to y, we're going to have a long 0. That's 0 error. This is basically the error. And if the y is bigger, this is going to be positive, and if y is less, this is going to be negative. Okay, so a residual plot, this is basically, we won't have to do this, but this is generated as part of error analysis if you're doing a software package and generating these things. It will give you a printout of this, and then basically you're going to go look and make sure these things, it's pretty much the error is kind of the same all the way through. Some places is high, but it's not all of them are high here, all of them are low here. It is just kind of a random differences, plus and minus. The spread is kind of the same throughout. So here the residual plot must not exhibit an obvious pattern. So all of them low here, all of them high here, and maybe all of them low, or all low here, and then all high here. The vertical spread of the points in the residual plot must be roughly the same across the plot. Okay, so it's kind of like the differences in here. You're seeing pluses and minuses, and there must be no outliers. All of a sudden, there's some dot way up here when most of them are here. Okay, so the residual plot of the candy products does satisfy all three conditions. We may assume that the linear model is valid, and we may construct confidence intervals and test hypotheses about beta 1. There's only one that we're going to be concerned about as we go forward. Okay. So first off, let's do a confidence interval for the slope. So we're going to go through two steps of this thing. The slope b1 of the least squares regression, this is the only one we're going to do a confidence interval hypothesis test for. So the slope b1 of the least squared regression line is a point estimate of the population slope beta 1. So we remember or recall, we're always, when I'm doing a confidence interval, it's always the point estimate in the middle. What's the point estimate here? It's going to be B1. And then I'm going to add a margin of error, subtract a margin of error. And that's how the confidence interval looks. This is a number line and some point minus the margin of error plus the margin of error. Okay? So first of all, we need to do this thing called the residual standard deviation. This is the residual standard deviation. Residual standard deviation. So this is one thing that you're going to have to do, remember in your formulas. There's S sub E. The sum of the y minus the y hats, those are the residuals. This is the actual, and that is the predicted value squared. Take the square root over n minus 2 in this case. That's not the standard error yet. You remember the standard error, the margin of error is something times the standard of error. Usually either a z alpha over 2 or t alpha over 2 times the standard of error, and this is the standard error formula. I take what I've just calculated and divide it by x minus x bar. So this looks the very same as this, except here's got the n minus 2 in there. So again, this is the data that we're talking about, the fat and the calories, and I would like to be able to predict the calorie values from some values of fat. Here's the predicted value. Notice that these are the actual values for the candy bars. We've got predicted values using our regression model. Here's the difference between the actual, this only makes sense, the residuals only make sense along where I've got these pairs. I can do the model, the predicted for anything. So this could be at 500, up here, anything 400, down here at 300. I could do a model. These aren't ordered, but I'm just saying that here's the pairs. But the residual only makes sense for where I've got an actual, and then I'm just going to test how accurate it is, build these errors, square them to make them all positive. If I did this, I'm going to get a very close to 0 value here. I need to square them, turn them all the same sign, and then I get my residual squared. That's the residual squared. That's that thing. Divide by 18 minus 2. I had a sample size. This is my n minus 2. There's 18. So I divide by 16, then take the square root, and I would have S sub E as that. That's the residual standard deviation. And then I would need to do S sub B to get my standard error of the S sub E, that value, and divide it by the x minus the x hat squared. Okay. So compute the standard error. Again, this is where we were. Oh, this was the x bar, sorry. X minus x bar squared. We do the x minus x bar and then divide that out. So here's our confidence interval. So basically this is going to be a little score, right? Our z-score / t-score. Which one is the better to use, the standard deviation or the standard distribution, or the student's t? Turns out the student's t's is better for this, and n minus 2 degrees of freedom. If I plotted all of these about with all the different samples and did B1s from these things, then this thing would show a standard t distribution, n minus 2 degrees of freedom. Critical value, t alpha over 2, t alpha over 2, that's just the 1 minus alpha. So I would go, how do I do confidence intervals? This is t alpha over 2 T alpha, this is like the minus T alpha over 2 df n minus 2. So it all depends on alpha, but I need those critical value. This is what I need to multiply the standard error by T alpha over 2 to get a margin of error. Okay. And then once we do this, again, here's our margin of error minus ME. This thing is plus ME. And that's what our margin of error looks like. Okay. So compute a 95% confidence interval for the slope beta 1 for the candy data. Okay, so here's the thing that we've already calculated. We get that pretty quick. Okay. Point estimate of B1, that's going to be there's our B1. The point estimate is B1. We've got that. The residual standard deviation was computed as SE. The standard error, that's what we had just calculated, 0.387349. Now we've got to have the T alpha over 2, so I go to the table, A3, 16 degrees of freedom, we had 18 samples for critical value, 95% confidence, so I had, let's go again, 0.95 on the inside, 0.05 on the outside. I'm looking at 0.05 over 2, that's T alpha over 2. So T alpha is 0.05, this is 0.025. 0.025, I'm either going to go get this one that's a negative value, or look at this as saying to the left is 1 minus 0.025. Okay. So once we find that, we go to the table, there's the 2.120, 2.120 minus 2.120. Multiply that by 0.3874349. That's our standard error, standard deviation, residual standard deviation. This was the standard error times T alpha over 2. That gives us the 0.82118. So I'm going to do, here was our B1. So B1 minus this. There's our margin of error. This minus that is the 4.812, and that's 6.642. So if we drew this out, here's a number line, down here is 0. We say this is 4.8182. This is 6.4605 on a number line. Somewhere in here, we can't say where, is going to be beta 1, the population slope, with 95% confidence. So that interval matches with 95% confidence. Okay, and how do we say it? We are 95% confident that the mean difference in calories for items that differ by 1 gram of fat content is between 4.8182 and 6.4605, or we can say that we are 95% confident that the true population slope beta 1 lies between 4.8182 and 6.4605. So on a TI-84, we can go down here. This is a linear regression T interval. L1, L2 for our values. Frequency 1, the confidence level, we gotta have that, and then do a calculate. Okay. The reason we point these out is, remember, you may be given these values on a test and asked to interpret it. You would have everything you needed. Okay. Since you're doing a T interval, that would be the T interval. That would be the beta 1 interval, confidence interval. Okay, here's our B, that's our slope. Degrees of freedom 16, I had 18 points. When we went down here, we entered 18. The R value, the R squared value, the R squared goes along with the model. And then the R is the confidence. So what about hypotheses? I told you we were only going to be worried about one. Test hypotheses about a population slope beta 1. In general, the one we're going to be worried about is beta 1 equal to 0 versus beta 1 not equal to 0, beta 1 greater than 0, beta 1 less than 0. And we can kind of base these on whether the sample B1 is greatly positive or greatly negative, or we just don't know it's close enough and we're going to testing that one. Okay. So here is our H0. These are H1s, right? These are our possibilities of H1s. Why are we concerned? Because this tells us which test. Right-tailed to the left is left-tailed, and not equal 0 is a two-tailed test. But this is always, or for what our concern is what we are concerning with beta 1. Okay? If we reject this, if we fail to, so let's do this thing. If I fail to reject this possibility, that means that there is no difference in terms of x. No matter what values of x, it's not going to change the b0. You remember I've got some y hat b0 plus b1x. If this is 0, which is what we're testing for in this hypothesis, it says no matter what x changes, the y value is not going to change. It's going to maintain b0, because 0 times anything is still going to, the whole thing is going to be 0. Okay? So if this null hypothesis is rejected, we get a rejection region or rejection that we're rejecting who? H0. We're rejecting beta 1 is equal to 0. That means there is some relationship. Okay? There is a linear relationship. As x increases, I'm multiplying it times some b1, positive or negative, and this thing either increases or decreasing, because every time I change x, I'm multiplying it, adding it to b0. And again, we start with this. Here's our test statistic. It's going to be a t-value, n minus 2 degrees of freedom. So I do this, I can calculate from here a p-val, or I'm going to use alpha and construct a rejection region by regions, rejection region / fail to reject. So either way, I can do this. Now, what is our hypothesis about beta 1? It's equal to 0. So this is basically 0, and I'm only left with that. So here's our test statistic. T equal B1 divided by S sub B. That's the standard error, not S sub B, which is the residual standard error, or the residual error, okay? So compute the least square regression line, verify that the assumptions of the linear model are satisfied, state the null and alternate. This is always going to be H0. Does beta 1, if beta 1 is equal to 0, there is no relationship between these two. Okay. If I'm going to do this, choose a significance level to make a decision. I always have to have some significance level. Compute the standard error of the slope. That's the SC. That was what? S sub E divided by X minus the X bar squared. Compute the value of the test statistic. If I do it by regions, I can do a left tail, a right tail, or a two tail. And then I'm going to plot my value of the test statistic in terms of here. have some fail to reject in the middle, rejection region. I'll put this as a question mark as a left-tailed, rejection region as a right tail, or both of them if I have a two-tail. Okay, so this is a little differently. I'm going to, you're either going to be given this, do it as a versus a left tail or a right tailed or a two-tailed. But here I would have something like if beta 1 was equal to negative 2.6 or something, some negative number, I'm going to do a left-tailed. If B1 is equal to 3.5, let's say, I'm going to do a right tail. And if it's further enough away from 0 and that right tail, then we reject. And then two-tail, I'll have something that's close or something. I'm just going to test if it's either way. Okay, but we can do a little better with these since we have the sample, but I may want to check just as a two-tailed. Left-tailed, here gets the full alpha value, the right tail gets a full alpha, and if I'm two-tailed, I do an alpha over 2 and then do a conclusion. Okay. So let's see if we can walk one of these things through. Here it was, we wanted to check on perform a test of H0 beta 1 equal to 0 versus H1 H0, the null, versus the alternate beta 1 greater than 0. We want to do a right tail. Since we got this as positive, let's go ahead and do a right tail. We know this thing is, from that sample, it's that right. We'll just see if it's further enough to the right to reject this possibility. There's our standard error of B1, that was S sub B, B1 over this. This is our test statistic. So we have a 14.56 test statistic. And then we could go through and find the t-value. Where is this? Find me the t based on n minus 2 degrees of freedom. And if we do this, so what's the probability? This is what we're saying. What's the probability of t greater than 14.56 df equal n minus 2? And we go to the tables. To the right of this thing would be a probability value of 0.597. Less than the alpha 0.05. That's what we're testing here. Here's the p is less than that. The p-val less than alpha, we reject H0. So what are we rejecting? That it is possibly equal to 0, that there is no relationship, there is no slope in this value. Okay? So we can conclude, since we reject one, we get the other one. And which one were we testing? The alternate of B1 greater than 0. Critical value method, everything is going to be the same, except first of all, we have to find the critical values, right-tailed. Nothing else is going to change except I want to do a T alpha. I go back, I look for the tail. All of this is 0.05, so 0.95 is in here. I go, and if I'm looking at the table with the probabilities to the left, I say, give me that critical value of DF equal to 16, and that would give me this thing of T alpha as 1.7456. So that line is 1.7456. Here's our test statistic, the very same thing. This is all the way out here. There's 0 at the hump, right? So where are we out here? That's rejection region. All of this to the main body part is the fail to reject. Reject, who do we reject? H0 always, never H1. So we rejected this possibility. at the alpha 0.05 level, there is sufficient evidence to support the hypothesis or the claim that beta 1 is greater than 0. There's sufficient evidence to reject the hypothesis that beta 1 is equal to 0. So here is, again, on the 84, if you go back through your stat test, the linear regression t-test would be the hypothesis test for this, okay? And here it gives you beta and beta not equal to 0, the greater than 0 test. Then we do the calculate. Here would be everything based on this. Don't worry about the row. Here's our beta. That's what we want to work on. Okay, p-value. We go down, continue, that little arrow says there, continue. We would have the p-value that p is less than our alpha, which is the 0.05. And then we would directly reject. So this is reject 80. This is less than 0.05. Is it? Yes, so we reject. So the correlation here is the Greek letter rho. That's the piece of it that was in there. We can do this as that goes into some of them. That gives you that one. So we're testing correlation, the very same thing. The rho equals 0. So here, when I'm testing this beta 1 equal to 0 is also a test of H0 rho equal to 0. There is no correlation. So as I change x's here, that's the same thing that if I change x, I don't get any corresponding changes in y. So I get this test for free. Okay, they're matched. Versus H1, that rho less than equal, greater than 0, not equal to 0 versus those. And of course, we have to set up critical values and the p-vals based on this. Okay. So R is our sample correlation, and the rho is the population correlation. Okay. So that's basically wraps up chapter 11. Got to go back through, spend some time in your labs, working some of these problems, get an idea, read back through the book. And since that's basically the end of the chapters, this is the last lecture. So good luck going forward, and hope to see you soon.